In this lesson, we are going to review some sample examples that cover the material from chapters 2 to 6, which will be on your first midterm. I've also included a study guide that is not part of this presentation, but just lists the topics that you should know and things that you should include on your note sheet. Where these questions came from is back when I taught this class in person, I would give weekly quizzes, and the questions in this review lesson are modifications of those weekly quiz questions. I can't promise your exam will be the exact same as this, but if you know these ideas, you should have a pretty good handle on the information and be able to generalize any questions that aren't explicitly exactly like these. So chapter 2 was titled Turning Data into Information. And one of the big ideas was the difference between populations and samples. So in each situation, state whether it would be more appropriate to treat the observed data set as sample data or population data. So is it just a subset that would be from sample data, or is it the population, which is all / everybody? So a historian summarizes the ages for all deceased past presidents of the United States. Well, if we care about presidents, this would be the population. We only care about presidents. A nutritionist wants to determine which of 2 weight loss programs is more effective. He assigns 25 volunteers to each program and records each participant's weight loss after 2 months. Now the question is these 50 people, 25 for each group, are they everybody you care about, or are they just a sample? And it's pretty obvious here that they are a sample. And the reason is that we did not assign all people in some big group. To be on one diet or the other. Another important classification was the difference between categorical variables and quantitative variables. So remember that a categorical variable means that you fall into one of 2 categories, and a quantitative is something that's in where you can have any specific number in a given interval. So there's not specific boxes that people fall into. So length of forearm from elbow to wrist. Well, obviously you have to have a positive length forearm and there's some maximum forearm, but anything in the middle is totally legitimate, so this is quantitative. And then favorite color for an automobile, obviously that is categorical. On your first take-home quiz, you were asked to give examples of different kinds of variables. That probably will be a good test question, so pay attention to that. Another important relationship that you were supposed to know is the difference between an explanatory and a response variable. Remember that the explanatory variable is supposed to sort of be related to a change in the response. So for college students, is there a relationship between grade point average and average number of hours spent studying? So does GPA affect grade point average? Does grade point average affect how much you study? Or does how much you study affect grade point average? And I would say how much you study probably leads to a response in grade point average. So the explanatory variable in this case is hours spent studying each week. And the response is grade point average. Another important skill to have is to be able to compute numerical summaries of data. And included in that is the numbers in a 5-number summary. And I'm going to just review what those are. 5-number summary, back before that was hashtag, that meant number, are the min, quartile 1, the median, quartile 3, and the maximum. You should know that for your test. And notice that one of those numbers is the median, and we are going to work on finding that one now. So to find the median, first you have to reorder the data. So the lowest number on this list is 102. Then next we have 110, 118, 122, 123, 127, 132, and 150. So I always like to check by counting. There are 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So the median is the middle, but in this case there are two middles. So to find the median, we find the mean, or we average those two. So the median is equal to 122 plus 123 over 2, which is 122.5. So next, let's find the upper and lower quartiles. So remember that our ordered list was 102, 110, 118, 122, 123, 127, 132, and 150. Now, the median was the average of these two numbers. When we find the quartiles, we still use 122 and 123. So there's our halfway. To find the lower quartile, we find the median here. To find the upper quartile, we find the median there. So quartile 1 will be the median of the first 4 numbers, and since there are 4 of them, we're going to have to average again. So 110 plus 118 over 2, which comes out to be 114. And quartile 3, once again, is an average, 127 plus 132 over 2, which is 129.5. Okay, next find the interquartile range. Well, the interquartile range is quartile 3 minus quartile 1. It's the distance between the two quartiles, or the part in the middle, inner quarters. So that is 129.5 minus 114, which comes out to be 15.5. One of our major uses of the interquartile range was to find any outliers in the data set. You will have to know how to find outliers on the test, and I will expect you to explain your work using numbers. So the way you do that is you look at Q1 minus 1.5 IQR. Anything below this is too low. And Q3 plus 1.5 IQR, that's the upper bound. Anything above this is too high. So since both of those things involve the IQR times 1.5, first thing let's do is find 1.5 IQR. So 1.5 times 15.5 is 23.25. And then we're too low if you're below quartile 1, which was 114, minus 23.25, which is 90.75. So there are no scores that are too low. You're too high if you're above 129.5, that's quartile 3, plus 23.25. Which is equal to 129.5 plus 23.25, 152.75. So that 150 is close, but no cigar. So thus there are no outliers. So I will expect you to make some kind of conclusion. The things I'm looking for here is the conclusion, and I need to see that you have the too high and the too low bounds correct. Another important numerical summary was the mean and standard deviation. Here I gave you the standard deviation formula. On your exam, you should put that formula on the note sheet because I'm not going to give it to you. Okay, so first to find the mean, we add the numbers all up and we divide by how many? So 22 plus 27 plus 30 plus 21, all divided by 4, works out to be 25. So there's the mean. Now, to find the standard deviation, the first thing you actually do is find the variance, which is the standard deviation squared. This is my preferred method. Start with this and then square root it to get your answer. And the way you find that standard deviation squared is you take all of your observed values minus your mean squared, and then divided by n minus 1. There's a technical reason why that's n minus 1, but I'm afraid it's incredibly theoretical. 22 minus 25 squared plus 27 minus 25 squared plus 30 minus 25 squared plus 21 minus 25 squared. All of that divided by 4 minus 1, or 3. So the variance s squared is equal to, well, first 22 minus 25 is negative 3, so that's 9, 4, 25, and 16, all divided by 3. So s squared equals 18, and therefore the standard deviation, which is s, is the square root of 18, or approximately 4.24. And a lot of you had trouble with this, so it's really the relationship between variance and standard deviation is not hard. To go from variance to standard deviation, you take a square root, like we did, root 18. If you want to go backwards to undo that, how do you undo square rooting? You square, as in, take your answer to the power of 2. That's how you go back and forth. Another important property we discussed was this property of bell-shaped data, that we have this rule that scores fall within plus or minus multiples of the standard deviations. So, for example, suppose that the distribution of verbal SAT scores is bell-shaped, has a mean of 540 and a standard deviation of 50. So 68% of the scores are going to fall between your mean plus or minus 1 standard deviation. So 540 minus 50 is 490, and 540 plus 50 is 590. All right, 95% of scores on the SAT fall between the mean plus or minus 2 standard deviations. Well, that would be plus or minus 100, so that's 440 to 640. And 99.7, meaning almost everybody, falls within the mean plus or minus 3 standard deviations. So if you're outside this range, 390 to 690, you're really special. I'm not even sure if that's theoretically possible. I don't know the highest score you can get on a verbal SAT. So ignore the reasonability part of the question. Just mostly I'm trying to get at what is the, how do you apply this rule? So the head circumference of adult males has a bell-shaped distribution with mean 56 centimeters and standard deviation 2. What is the head circumference such that only 2.5% of adult males have a smaller head circumference? So I like a picture, and I need a symmetric thing to draw around. All right, so plus or minus 1 standard deviation, just assume this is symmetric. We have 68%. Now what that means is that this percentage and this percentage total to 32, with half on each side, and 32 divided by 2 is 16. So we have 16% over here and 16% over there. And actually that's going to answer this question. What is the head circumference such that only 16% of adult males have a larger head circumference? Well, this is 56. Standard deviation of 2 makes this 58. If you're at 58, only 16% of people fall over here above you. So the answer to this question is 58 centimeters. So at 58 cm, only 16% of men have a bigger head than you. Note that means in the actual physical sense, not like the mental sense of being full of yourself. I don't know how we measured that one. Now the first question said, what is the head circumference such that only 2.5% of adult males have a smaller head circumference? Oh, and no, nothing dissing males there only. Okay, I know I'm a girl, but I was just trying to make a bad joke. So it's the same kind of picture, except for we know that plus or minus 2 standard deviations, we have 95% of our data, which means that over here lives 2.5% and down here lives 2.5%. So the head circumference such that only 2.5% of adult males have a smaller head circumference means we're at this data point. Well, if this is 56, this is 54, and that's 52. And if you land right there, only 2.5% of people are below you. So at 52 centimeters, only 2.5% of men have a smaller head than you. And another important skill you have to learn, this is the final one for chapter 2, is how to find standardized scores and interpret a little bit what they mean. So suppose that the mean weight for men 18 to 24 years old is 170 pounds and the standard deviation is 20. Find the standardized z-score for the following weights. So the formula for z-score is your x value minus your mean over your standard deviation, which if you use the symbols for sample data, it's x minus x bar over s. I mean, that's about equal to. But we're told the true mean, that's our mu, Greek letter for m, and this thing, standard deviation, sigma, Greek letter for s sound. So we have 110 minus 170 over 20, which is negative 60 over 20 or negative 3. Now what this means is that this person is 3 standard deviations below the mean. Yes, this is unusual. I didn't explicitly ask that question here, but remember that if you're 3 standard deviations below the mean, 99.7% of all people fall within that plus or minus 3, which means that you're in the bottom 0.15%. That makes you special. Okay, now how about 300 pounds? Well, same idea. We take 300 minus 170 over 20. Well, 300 minus 170 is 130. And 13 over 2 is 6.5. So this person is way off the top end, super far. So 6.5 standard deviations above the mean. So just a note that if you are less than plus or minus 2 standard deviations above the mean, you're not special. And I don't mean like you're not a special person, I just mean that you're not unusual. Maybe special is the wrong word. You're not unusual. So just keep that in mind when you compute standard deviation. If standard deviation is 1, well, you're 1 standard deviation above the mean, but you know, that's not all that uncommon. So next we talked about relationships between quantitative variables and regression lines. So one of the first things is what is meant by a positive association, a negative association, or none. So positive association means as one variable goes up, the other tends to go up. A negative association means as one variable goes up, the other goes down. And no association will look something like your 2-year-old throwing paint at a wall, all over the place. So forearm and foot length. Well, if forearm length increases, do those people tend to also have a bigger foot? Yes. People that have big arms tend to have big feet. People that have small arms tend to have small feet. So positive. Think to yourself, if you were going to plot points that were forearm length and foot length, it would look like this picture. So people with longer forearms tend to have longer feet. Not always, but this is certainly true on average. Okay, miles of running per week and time for a marathon. So just to think a little bit, like first this question duped me because I thought, oh, I get faster. So as I run more, I get faster, and that's positive. But getting faster means your time gets smaller. So that actually is a negative association. As miles run per week goes up, time goes down on average. I mean, there are certain limitations and stuff like that. I will never run a 2-hour marathon no matter how much I run per week. But on average, if you run more, you tend to run faster. A regression equation for y equals stopping distance, which is measured in feet, and x equals speed in miles per hour is given below. Notice that this could also be written as y hat equals negative 44.2 plus 5.7x. And I'm probably going to tend to do it that way, even though your book doesn't. So find the slope and interpret it in terms of how average stopping distance changes as speed increases for a car. So first of all, the slope is 5.7. Congratulations, you found it. You get 1 point out of 3. Now you have to interpret what it means. That is the more important component of this lesson. So remember that slope is change in y over change in x. So the units of this thing are y's units over x's units. So y is measured in feet, x is measured in miles per hour. So this is like 5.7 over 1. If miles per hour goes up by 1, then feet goes up by 5.7. So, and miles per hour was your speed. So if speed increases by 1 mile per hour, average stopping distance increases 5.7 feet. I mean, this is the reason why when you're driving in traffic, if you're going fast, you should allow more space between yourself and the car in front of you. The faster you go, the longer it takes you to stop. This just quantifies that relationship. What is the estimated or average stopping distance when the speed is 80 miles per hour? We'll just plug that 80 in for the x. Y hat is minus 44.2 plus 5.7 times 80. And that works out to be 411.8 feet. And notice that they use the word average here because this is the stopping distance of an average vehicle of this type. I didn't specify what kind of vehicle it was, but it could be, say, a car. And not all cars will have the exact same stopping distance. So this is just the average. If you're going 80 miles per hour, you need that many feet to stop on average, sometimes more, sometimes less. So suppose the stopping distance when driving 20 miles per hour is 50 feet. What is the prediction error, or the residual, for this speed? Now remember that a residual is equal to y minus y hat. So we need to find both y and y hat. Well, y is the actual value that we were given. We were given that when you go 20 miles per hour, this particular car stops in 50 feet. To find y hat, you estimate what you would have gotten for this average stopping distance using your regression equation. So plug in 20. Negative 44.2 plus 5.7 times 20 works out to be 69.8. So y minus y hat is 50 minus 69.8, which is negative 19.8. And how does this car compare to other cars? Well, this car has a lower or smaller stopping distance than the average car at this speed. Would it be appropriate to use this regression line to estimate the stopping distance for a motorcycle? And I think I specified that this was cars, but I think I probably didn't do a great job at that. So we are going to assume that this is for cars, and I'll be more careful on exams. So know the data used to make the regression line. used cars. And that means it applies to cars. Now, what kind of cars is a bit more specific, I need to be more specific, because if I only looked at sedans, this wouldn't apply to trucks either, because trucks are bigger and I think that they take longer to stop. So, but a motorcycle definitely is not the same as a car. All right, finally, what is the y-intercept, and does this have any meaning? So the y-intercept, the number you used for that in algebra was b, negative 44.2. So congratulations, 1 point, you found it. Now make sense of what it means. So this means when speed, which is x, is equal to 0 miles per hour, stopping distance is negative 44.2 feet. Obviously, this makes no sense. And what I'm looking for you there is that you understand that the y-intercept is when x is equal to 0. That is what a y-intercept is. And then you can interpret what those numbers are, write me a sentence, even if it makes no sense, and then tell me that it makes no sense. That's all you gotta do. All right. So the way we find these least square regression lines is by minimizing the sum of squared errors. And you never have to do this by hand on an exam. I know you had to do it on your take-home quiz, but you won't have to do it on the exam. But I just want you to be familiar with what is meant by the sum of squared errors. So let's review that quick. So first, find the value of y hat for each data point using this regression line. So x, y hat. So if x is 1, plugging 1 into that equation, we get y hat as 5. If x is 2, we get y hat is, so 4 times 2 is 8, plus 1 is 9. If x is 3, 4 times 3 is 12, plus 1 is 13. And if x is 4, y hat is 17. Okay. Part B says to calculate the sum of squared errors. So the errors are how different your estimates are from your actuals. And the reason you square them is so that negative, like underestimates, don't end up canceling positive estimates. So the formula for sum of squared errors is the sum of your y's minus your y hats squared. So the first y is 4, the predicted y is 5. Then we have 5 minus 9. And then we have 10 minus 13. And then we have 16 minus 17. So this is negative 1 squared plus negative 4 squared plus negative 3 squared plus negative 1 squared, which is 1 plus 16 plus 9 plus 1, 27. So that's our sum of squared errors. And one other thing that squaring kind of does is it sort of emphasizes the bigger differences. Like this difference of 4 contributes that lots, that's 16, whereas the differences of just 1 don't contribute very much. And one quick related question, if line 1 has SSE, not SEE, 27, and I gave you another line, line number 2, with SSE 10, who better? The answer is line 2. Smaller SSE means you've made smaller errors, your points are closer. That's the kind of question you have to be able to figure out for the test. Which one's better, or maybe even find the SSE. Okay, r squared. If r squared is 1, what are the possible values for r? So quick review, remember that r is this correlation coefficient, and it measures the strength plus direction of relationship. And note that r is in between -1 and 1. That's where r lives. To find r squared, you square this number. When you square, that r squared ends up between 0 and 1. So if r squared is equal to 1, to go back to r is equal to either +1 or your r was equal to -1. You had either a perfect positive relationship or a perfect negative relationship. Positive association, negative association. And don't forget to review the part in your notes that talks about the percent of variability of y explained by knowing x. That's what r squared is. Okay, now one thing you should know how to interpret is when is the r going to be bigger, when is it going to be smaller, when is it positive, when is it negative? Well, first of all, the positive and negative should be pretty easy to pick out. When those points sort of go down as you go from left to right, you have a negative r. So we think that, I told you that these are the possible r's. And tell me which one of those is graph 2. Well, that's obviously r equals -0.9. And just note, the reason that it's -0.9 and so close to 1 is that those points almost fall exactly in a straight line. So that's why that number is so close to -1. Okay, now the next 3, well, 2 of them have positive associations, and that's this guy and this guy. You can see that the numbers tend to go up, the numbers tend to go up. But graph 4 has more spread. And more spread implies lower r, as in closer to 0 in this case. So graph 4, the r is 0.3, and graph 1, the r is 0.6. And then graph 3, well, slope 0. That one is r equals 0. Knowing something about x doesn't change. Like if I know this x, this is my y. If I know this x, my y, you get no information about y by knowing x. So after talking about relationships between quantitative variables, we talked about relationships between categorical variables. So this is when your variables are only categories. So here we have a 2012 survey of internet users done by the Pew Center, and respondents were asked whether they use social networking sites. And of course, this is 2012, so these numbers probably have changed by 2016. So the following 2x2 table of counts displays the results by the sex of the respondents. So calculate the row percentages and then explain what they mean. So I'd like you to actually make a table. Okay. So of the men, what proportion said yes, they use social networking? Well, that was 525 over all the men, which is 846, or approximately 62.1%. And the men that said no, 321 over 846, which is about equal to 37.9%. Notice that that row should add up to 100. Now, of the women, 679 of the 956 surveyed, which is about equal to 71.0%, they said yes, and 277 out of 956, which is about 29%, said no. So what do these row percentages mean? So these give the proportions of each gender that do and do not use social networking sites. All right, calculate the column percentages and then explain what these mean. So keep the table's organizational structure the same. Men, women, yes, no. This time our totals are taken out of the columns. So out of all the people who said yes, what proportion were men, what proportion were women? So, well, 525 of the 1,204 yeses were men. This is approximately 43.6%. And you shouldn't take my word for it. You should actually probably pause and just make sure that you get the same numbers. And then 679 out of the 1,204, or 56.4%. Now, of the no's, 321 of the 598 no's were men, which is about 53.7%. And of the women, of the no's that were women, are 277 over 598, which is 46.3%. And so what these mean, this is the percent of the yeses that were men versus women, and the percents of the no's that were men versus women. Or you could say something like it's the breakdown of the yes category by gender, breakdown of the no category by gender, something like that. Now, one potential problem with column percentages like this is if these totals, the men and women, have been really different, that might skew this. So really, to look at the relationships, you should look at the row percentage. So does there appear to be a relationship between gender and social networking site uses? Look at part A. You need to look at it by gender. So the idea here is it breaks down by gender. And so, we didn't do a chi-squared test, but this is kind of just like a, what do you think? Maybe yes, no. And I would say maybe yes. Because the difference there is 71 to 62, it's about 9%. It's kind of a big difference. 9% more than men. But you would need a chi-square test to be sure. Although with a sample size that big, I'm pretty certain that a difference of 9% is going to be statistically significant. The following table is a table of data collected on smoking and whether or not the subject had ever been divorced. So use the data in this table to compute the following. So the risk of being divorced if you're a smoker and if you're a non-smoker. So the risk for a smoker of getting a divorce is computed by figuring out how many smokers have been divorced. So here, I know it's a bit confusing, but this is referring to those things, and this is referring to these things. So if you're a smoker, you live in column number 1. This is the row number 1. This is the smokers. So the number of smokers who have been divorced is 238 divided by the total number of smokers, which is 485. That works out to be approximately, let's just do 3 decimal places, so 238 divided by 485 is 0.491. And the risk for a non-smoker, well, of the non-smokers, 374 had been divorced, but that was out of 1,184. Which is a risk of 0.316. So that appears to be that non-smokers have a lower risk of getting divorced. So the relative risk of being divorced for smokers compared to non. So the relative risk is equal to the risk for category 1, which was smokers, over the risk for non. Well, that's 0.491 over 0.316, or 1.554. So what that means is a smoker is about, around here, 1.5 times more likely to get a divorce than a non-smoker. Finally, part C, we want to know the percent increase in the risk for smokers compared to non-smokers. Well, the way you find percent increase is you take the relative risk minus 1 times 100% to make it into a percent. So that's 1.554 minus 1 times 100%, or 55.4%. So the actual way you quantified whether or not a relationship existed is you use this thing called the chi-squared test. And there were 2 things you could use to check that. First, you find the chi-squared value, and then you find the p-value corresponding to it. And because we're working with a very, very simple case, you know which chi-squared value is your cutoff. But I care that you also know the p-value cutoff as well. So for the p-value cutoff, you reject H naught if p is less than 0.05. Sometimes you make it more stringent than that, but that's the general rule of thumb. So if your p-value is 0.055, is that less than 0.05? No. So in this case, you cannot reject H naught, or you fail to reject H naught. One thing to note, this does not mean H naught is true. That is not the case. You just don't know what to do about it. Okay, so for p-value, you're looking small. P-value, you want small. chi-square, you want big. And I'm going to say big in quotes there because in this case, big means greater than 3.84. So is this chi-squared bigger than or equal to 3.84? The answer is no. And that means you cannot reject h0. In this case, chi-squared is bigger than or equal to 3.84, and you can reject h0 in favor of HA. We'll deal with other chi-squared tests in the very last unit of this chapter where we have bigger than 2 by 2 tables, and in that case your chi-squared, how big it has to be to have a low p-value, is even bigger than 3.84. It's just the stuff you're doing now is always 2 by 2 for this reason. The other stuff is more complicated. Okay, so let's do an actual chi-squared test. The following two-way table of counts summarizes whether respondents smoked or not and whether they divorced, so same example as before. And I'd like you to write null and alternative hypotheses about the relationship between the two variables. So the null hypothesis is always one of no relationship. So in this case, our variables we care about relationships between are smoking and divorce rate. There is no relationship between smoking and divorce rate. And HA is just the alternative. There is a relationship between smoking and a divorce rate. To test whether this is a relationship, we use the table of expected values, and remember the formula for that is row total times column total over the total. So we have the yes and the no's, and the yes and the no's. Okay, so the row total is 485. Column total is 612 over 1669. It's important you round these to 2 decimal places. So 177.84. And then row total times column total over here, 485, 1057 over 1669, 307.16. Okay, in the nose, row total 1184, column total 612, over 1669, 434.16. Row total 1184, column total 1057, over 1669, 749.84. So there are what you would expect to see on average if there was no relationship. So just looking at your table, the numbers in the expected values seem to be a bit different than the ones that you actually observed. Find the value of your chi-squared statistic. Well, the formula for that is the sum of observed minus expected squared, all divided by the expected value. So chi-squared is observed, which is 238, minus expected, which is 177.84 squared, over 177.84. plus the next observed, which is 247, minus 307.16 squared over 307.16, plus, next we have 374 minus 434.16 squared over 434.16. And then we have, lastly, 810 minus 749.84 squared over 749.84. And I would go ahead and pause and make sure that you can put this thing in your calculator sort of all in one go. And this should have been a 749, bit of a boo-boo. I got a humongous chi-squared. I got chi-squared equals 45.297. Huge! So can you reject the null hypothesis? Why or why not? So yes, the reason why is that the chi-squared is bigger than 3.84. So you reject H naught in favor of HA, and there is an association between smoking and divorce. Well, it doesn't mean that smoking causes divorce. It just means that smokers tend to get divorced more often than non-smokers. All right, the final unit, or the final set of chapters here are Chapter 5, which talks about sampling and surveys, and Chapter 6, which talks about various types of studies. So one important idea in this stuff is the idea about bias and knowing what different types of bias are. So question here is, what type of bias do you think is going to be introduced in the following situations? So possible answers are selection bias, non-participation bias, and response bias. So first, a list of registered automobile owners is used to select a random sample for a survey about whether the people think homeowners should pay a surtax to support public parks. So selection bias is when you somehow select the wrong sample. Non-participation bias means that people don't participate. And response bias means that somehow the response they give you is messed up for some reason. So this to me looks like selection bias. And that's because automobile owners might not represent your entire population, especially if you're talking about a big city where lots of people might not own cars. So this is selection bias. So not all homeowners may own cars. Or just not all taxpayers, not all people. A survey is mailed to a random sample of residents in a city, asking whether or not they think the current mayor is doing an acceptable job. Well, this is probably going to suffer from non-participation bias. And the reason being is that many may throw the survey out. So in an ABC News poll, a random selection of 1,006 adults were asked, compared to buying things by mail order or in a store, do you think that buying things over the internet poses more of a threat to your personal privacy, less of a threat, or about the same? Of the people surveyed, 47% said that this was about the same. So first, what is the margin of error for this poll? Well, the margin of error formula, the crude one we use, is 1 over root n, or 1 over root 1006, which is approximately 0.0315, or about 3.2%. What is the conservative 95% confidence interval for the population proportion that would have responded about the same? Well, that is found by taking 47% plus or minus this margin of error, 3.2%, or gives us an interval from 43.8% to 50.2%. What sample size produces the following margin of errors? This is a really good question to ask. If you want this margin of error, what should be your minimum sample size? Now to do that, we solve the equation 1 over root n equals 0.05. So I'm going to multiply the root n over. That gives me 1 equals 0.05 times root n. I'm going to divide by 0.05 and I get 20 equals square root n. And then I square and I have n is equal to 20 squared or 400. So n needs to be 400 to ensure that my margin of error is at worst 5%. Margin of error of 30%, not sure why you'd want that, but here's the basic idea, same thing. 1 over root n is 0.3 multiplied by root n. 1 equals 0.3 times root n. Divide by 1, you get 3.333 repeating equals root n. Square both sides, and you get n equals 11.111, etc. Now, you have to, in this case, round this up to 12 because you can't ask a tenth of a person. So you have to take 12 people. And the reason you don't round down is rounding down would put you below that threshold. So to ensure you're within it, you always have to round up in these cases. It's also pretty useful to know the differences between certain kinds of samples. So in each part, identify whether the sample is a stratified random sample or a cluster sample. A class of 200 students is seated in 10 rows of 20 students per row, and 3 students are taken from each row. So stratified random means first you break into strata. So break into strata, then pick. Cluster sample means you pick in groups. Like break into strata and then pick one of your strata, something like that. So this one, because it's 3 people being picked from each row versus a few random rows being picked in their entirety, this is a stratified random. The rows are your strata. You could make it cluster by choosing, I don't know, say 3 random rows. That would then be a cluster sample. An airline company randomly chooses one flight from a list of all international flights taking place that day. All passengers on the selected flight are asked to fill out a survey on meal satisfaction. This is a cluster sample. One flight is the cluster. In each part, indicate whether the sample should be called a self-selected sample or a convenient sample. So did people choose to participate, or was it just easy for you to ask these people? A political scientist surveys the 80 students in his class, and he teaches to evaluate student political views. This seems like a convenience sample. nothing says people in his class, I mean, they might have some kind of bias that we don't know about. A soft drink company wants to know which of their two drinks customers prefer. They make a table at the mall, and people who are passing by can stop and participate in a taste test if they wish. The sample consists of those who agree to participate, so this is self-selected, as people select themselves to participate. And that's the end of my review lesson for you guys. So make sure that you have a note sheet for your exam and that you bring a calculator. Good luck.